In Module 2, I'll talk about measuring volatility, and of course the notion of measuring volatility, there's really two sides of it. Module 1 looked at the measuring implied volatility, which is measuring the market's estimate of prospective volatility by virtue of looking at options that are trading in the market and using a Black-Scholes or other formula to reverse engineer what volatility would in fact provide the market prices that are being observed. In this module, we're going to look at measuring volatility as in terms of historical volatility. So again, we go back to the typical price process. This is a slightly more general one. Our typical sigma function is in fact simply a constant sigma times S. But this is slightly more general. It's not terribly important for the purposes of this module, but one might imagine that you have a stock price process where sigma is not a function, is not a constant times the stock price, but in fact sigma might depend on stock price, it might also depend on time, or it might depend on some econometric variable X, inflation, GDP growth, what have you. And so this is just, if you will, an econometric model for how one might think of generalizing a geometric Brownian motion, and to say if we're going to measure sigma, sigma could be a very complicated function depending on many variables. Of course, in general, we don't have much hope. This is a notational device by way of saying we recognize sigma could be quite complicated, but it doesn't provide us with a mathematical tool for actually evaluating what this complicated or this complex function might be. That in general, our historical estimations are going to be relatively simple in the sense of we're going to calculate volatility using standard statistical calculations, and to the extent that we want to appreciate the time dimension of volatility, if we want to get away from a constant sigma idea, what we usually do is look at historical periods split into subperiods to see how variable our estimates might have been in different periods of time. The typical approach, and this is consistent with the fact that prices in geometric Brownian motion in the Black-Scholes model, but also prices in our binomial trees are modeled to be log-nominally distributed. And that is, ultimately, we're interested in sigma being a measure of the variability of the return on stocks. And so it's only appropriate to actually do an estimate of that statistic in historical data, and that is where we define the random variable here, epsilon, at time t plus h, is nothing more than the log ratio of stock price at time t and the stock price at time t plus h. And of course, this is consistent with the model that st plus h is equal to st times e to this term. So in this model, this epsilon term, this epsilon term is in fact not an annual return. And we'll fix that later. It's a period return, so that the numerical size of this variable very much reflects h, the length of the period. Ultimately, what we want to do is annualize these values, because you remember in all of our models, we actually have an h in the exponent. What we would rather say is that s at time t plus h is equal to s at time t times e to the h return, where r now is an annualized return. So we'll need to do we'll be looking for an annualization process here, that the way the model is set up is it actually gives us the random variable e, which is by definition the period return. In all of our modeling in Black-Scholes as well as in our binomial trees, we actually are looking for an annualized version of that, where we build the time factor h right into our exponent.